Let's study our first design strategy, incremental approach. We're going to talk about the design and analysis of incremental approach with a very important technique, loop invariant. So let's first look at the example insertion sort. As we all know, the problem sorting takes a sequence of n numbers as its input, and its output is a permutation of the input sequence. If we denote the output as a1 prime, a2 prime, and an prime, then we want them either in ascending order or descending order. Let's say ascending order, which means a1 prime should be smaller or equal to a2 prime, and so on. The idea of insertion sort is quite simple. We're going to look at the elements from the input sequence one by one. For example, when we look at the element a sub j, we assume the elements we have seen so far, which means from a1 to aj minus 1, we already sorted them. So when we look at the element aj, we just need to insert aj into the correct location, and then we have the subsequence from a1 to aj sorted. So we can use this chart to help us understand this idea. The cards in the left hand are the elements we have seen so far. They are in order already. The card in the right hand is the one that we want to insert at this time. If we put this idea into an array representation, we have this chart. So we have all the input elements in A from 1 to n, that's the entire array. Currently, we want to look at the element A sub j. So I put a yellow element there. And then the elements from 1 to j minus 1, we assume we already sorted them, so they are in sorted order. Now, let's suppose the correct location of A sub j is right after the element ai. So what we need to do with array representation, we need to make a room for aj to be inserted to the correct location. So here are the steps. So first of all, we need to copy the value of A sub j to a temporary variable key. And then we need to move all the elements from a I plus 1 to a j minus 1. These elements are all greater than value key. So we need to move them to the right and make room to insert the value of element A sub j, which is key. So that's the whole procedure of this insertion sort. We have a pseudocode to just reflect the idea we talked about. So here we have a main loop, which is for loop, and the loop variable j goes from 2 to the last element of A. We don't start from 1 because the first element by itself is already sorted. And we put A sub j to key to store this value temporarily. And then from line 4 to line 7, we're going to make a room for the value key, the correct location. And this while loop basically gonna move all the elements that are greater than the value key to its right. And finally, we put key back to a I plus 1 position. Note that the while loop, actually there are two cases the while loop going to terminate. The first case is we find a element, ai, that is smaller or equal to key. So we're going to stop, and we need to insert key right after this ai. Second case, we run through the entire array and all the elements are greater than key. So I becomes 0. For that case, we just insert the key to the very first location of array A, which is A1. Okay? Let's look at an example. We have an input array of 6 elements, 5, 2, 4, 6, 1, 3. The first element by itself is already sorted. So the for loop starts from the second element. Value of second element is 2. Now, after we copy 2 to another position, we now enter to the line of 4 to 7. Basically, we need to find a room to insert our element 2. So the first element we check is 5. 5 is greater than 2, so we need to move 5 to its right. And we did that. After that, we reach to the end of the array, so we need to put 2 back to the first location of the array. And here is what we get after that step. Now, 2, 5 are in sorted order, so the pointer moved to 3. So the third element of the input array, and the value of A3 is 4. Again, line 4 to 7, going to check and find the correct location to put back 4. And you're going to start with 5. 5 is greater than 4, so 5 is going to move to the right. 5 is going to move to the right. And 2 is smaller than 4. The while loop is going to stop at this position, and we need to move our value back to this position. So here is what we get after this iteration, and so on. So we're going to stop here. If you're interested, you can check the textbook to see the rest of the execution. Again, let's summarize this incremental approach we have seen so far. So first of all, we see a main loop. In this case, that's the for loop. And then we solve the problem by incrementally growing the solution, which means we make A1 sorted, and then A1 to A2 sorted, and then from A1 to AJ sorted, and at last A1 to AN sorted. So that's the idea of incremental approach. However, here there's a very important assumption. The assumption is when we insert element AJ, we assume all the elements from A1 to AJ minus 1 already in a sorted order. Is that a correct assumption? How can we make sure this assumption always true before we enter the for loop, right? Okay, so here is the problem of verification. We're going to use mathematical induction to help us make sure the assumption that we made before the execution of the for loop is correct. And that technique is called loop invariant. And after that, we're going to talk about how to design an incremental algorithm given precondition, given a postcondition, and also given the loop invariant.